Okay, so this is an example where we get to use potential energy multiple times, multiple kinds of potential energy to solve a problem. So elastic potential energy and gravitational potential energy, and then there's some friction added in at the end. So in part A, we're asked, okay, let's do the setup. So a block of mass m is held against a spring of spring constant k, which has been compressed to distance x sub I for x initial. And we want to derive formulas for the following. So in part A, the block is released from rest from this spring, and it starts sliding across the frictionless ground. And what's its speed v once it's no longer compressing the spring at all? So it's its speed v at this point. So let's call this our initial place, and this is our final place, and we're going to use conservation of energy to solve this. So U initial plus K initial has to equal U final plus K final, and we're told that the block is released from rest, so K initial is 0. And then in our final situation, we're ignoring the spring, we're not doing anything with the ramp, so we'll say that U final is also 0. So, so conservation of energy gives us basically that U initial has to equal K final. So our initial potential energy is spring potential energy, and that's the only kind that we have right now. So 1/2 kx initial squared has to equal our final kinetic energy, which is 1/2 mv squared. And we want an expression for v, so these 1/2s will cancel out. We can divide both sides by m and take a square root, and we're going to get v equals square root of k over m x initial. Okay, now in part B, now the block starts sliding up a frictionless ramp. However, the ramp has an angle of theta, makes an angle of theta with the ground, and what's the farthest up the ramp it's going to go? And so now I'm talking about a slightly different situation, so I'm going to move this final position. I'm going to say now my final position is over here up the ramp. I'm going to leave my initial position as on the spring. If you wanted to, you could call this your initial position, and it should work either way. That's sort of your choice, but I'm going to do it this way, leaving the initial position as the compressed spring. So again, we have conservation of energy, so we have some initial potential energy plus initial kinetic energy has to equal final potential energy plus final kinetic energy. And again, we said we start out at rest, and we're also interested in how far up the ramp the block goes until it loses all of its speed. So K final is also going to equal 0. And so what we're saying basically is that our initial spring potential energy over here has to be equal to our final gravitational potential energy over here. So 1/2 kx initial squared has to equal mgh. That's my usual expression for gravitational potential energy, but mgh, this is h, and what I actually wanted was the distance up the ramp L, so I'm going to do a little bit of trig over here and say that h equals L sine of theta. And so then I can plug that in here. So mgh is the same as writing mgl sine theta. So if I want to solve for L, I can just do that. So I get L equals kx initial squared over 2 mg sine theta. Okay, so part C is a little bit more complicated. So part C says it's sort of the same situation as part B. I want to know how far up the ramp the block will go. But what if now the situation is not frictionless? What if actually this ramp is like a little bit rough, and so the whole way up the ramp the block is experiencing a friction force? Now we know we're losing some energy to friction, so we can't do conservation of energy the same way that we did before. We have to account for friction somehow. And we're able to do that because we're told what the friction is. We're told we can model the friction as just a constant friction force as it slides up the ramp. So now we're going to do the same thing, except we have to include the work done by friction here. And this is just like our initial work kinetic energy theorem, but now we're expressing work done by the gravitational force and the spring force in terms of potential energies, but we can't express the work done by friction in terms of a potential energy, so we just need to calculate out the work. So it's the same situation. K initial and K final are both 0. My initial potential energy is 1/2 K initial squared. The work done by friction is going to be a negative force of friction times the distance that the friction acts over L. And that has to equal the final kinetic energy, mg, or sorry, the final gravitational potential energy, mgl sine theta. Now the negative sign here in front of the work done by friction means that friction is taking away energy from the block. So it's decreasing the amount of energy that the block has. Another way of thinking about it is that as the block moves up the ramp here, it's moving this way, but the frictional force is acting that direction. So when the force and the direction of motion are opposite, then the work is negative. Okay, so now we just need to solve for L. So I'm going to move this term over to the other side and pull out the L. So we have 1/2 K x initial squared equals L times mg sine theta plus force of friction. So L equals K x initial squared over 2 mg sine theta plus the force of friction. And we can do a little sanity check here. This is essentially the same expression that we had in the previous case, except now the denominator is a little bit larger. And so if the denominator is larger, that means that the number is going to be smaller, and so the block will go smaller or shorter length L along the ramp when you add friction. And so that makes sense. We can do a little sanity check there.